In this video, I'm going to show you how to run a permutation test and also show you that I've learned a couple new tricks on how to run presentations in RStudio using a Markdown presentation. I haven't totally learned everything yet though, so you can also display these in HTML, but I haven't figured out how to make the pages the right size. So I'm talking about permutation tests today because I had someone ask us to help with a project, and their project involved some really non-normal data, and we were looking up ways to deal with non-parametric type data that we didn't really want to use log regression for. So as I get going, I'll show you kind of what we discovered and how these tests work. So a little bit of background information. I took most of this from Hal's website. The section that he has covering permutation tests and randomization tests is really fantastic, and it's written in a really easy style to understand. So everything I have kind of pulled on the background for permutation tests is on this link here that you can download. I'll also include this presentation and the data from this presentation on our Stats Tools website, which we're currently updating and hopefully should be done with this week. So I'm going to talk a little bit about random assignment and selection and compare this to a traditional null hypothesis testing design, a little bit on assumptions and null hypotheses as part of statistical tests. So starting with random selection and assignment, generally we want random sampling. So one of the crux of the ideas for null hypothesis significance testing, which is NHST here, is that we have randomly sampled from this population. So it's all about comparing things to populations. We pull this sample of people that we think represents our population, and that we're going to estimate our population numbers, our parameters, from this sample. And so we're drawing randomly from an intended population. And that's very important for null hypothesis testing, but we often kind of brush it aside. Because random sampling is generally not possible, too expensive, or just not practical. And so that can actually cause a lot of problems with non-representative samples. But we talk about it and then we kind of go, we can't do much about it. But in a permutation test, there's actually no concern about a population. So one of the biggest differences between these two in a sort of theoretical focus is that they really are estimating on the sample. So we're interested in this sample, don't care about this population. Who is this population anyway? So who cares about populations? So maybe we don't need random sampling because we're not really concerned with the larger population at play. And that is very different thinking. So one thing I had trouble with, because I'm a traditionally trained statistician, I train my students in traditional null hypothesis testing, even though I don't think it's necessarily the best solution, is that you have to stop thinking about, I am estimating from this sample to apply it to some pie in the sky population. Instead, we're just looking at this sample because they are who we're interested in. And I think I have a pretty good example of this coming up. Now, random assignment, however, is important for both tests. There is some work that says that maybe random assignment isn't totally necessary for permutation tests to still be accurate, but random assignment is pretty important when it comes to like scientific process and theory to ruling out other interpretations. So when you're able to randomly assign, you should. Now, when you're working with quasi-experimental variables like gender, or in the example I'm going to show you guys, what version of the class that I taught, you can't really randomly assign. But random assignment is still crucial to both types of testing, traditional null hypothesis testing and permutation tests. Random sampling is more important for traditional tests. And so when we get into like assumptions of tests, because this is often where you get stuck. So you have the sample that is a hot mess, or normal, because samples never follow this like perfect distribution, and you're kind of stuck. Like, well, what do I do? How do I test a two-way interaction when I have really messy data? And there aren't really good tests for non-parametrics when you're dealing with your traditional two-way ANOVA. Most people argue you should do log or permutation tests. And one of the biggest problems with log is the interpretation. And if you have truly continuous data, log won't really work because log really requires some like categorical data. And so you kind of get stuck with this, like, I don't really know what to do. So an option could be permutation test if you're willing to accept the theoretical underpinnings of that test. Cat is very interested in our presentation today, so you'll hear him walking around. So the assumptions that we normally are dealing with is normality, right? That the sampling distribution is normal. So the population doesn't really need to be normal, but the sampling distribution should be. And then homogeneity or homoskedasticity, kind of depending on what you're doing. So we do sometimes assume that populations are normal, although really what we assume is that the central limit theorem will help us with our sampling distribution. So we actually need the sampling distribution to be normal. And we assume that the populations are homogeneous. So that the variances are equal or that the residual error variances are equal in null hypothesis testing. So generally we can kind of get around some of this normality stuff by having at least a sample size of 30, where the central limit theorem really helps us out and says the sampling distribution is normal even if the population isn't normal. But if I'm working with a permutation test, there's no population assumption. So I don't have to really worry about either of these things because I don't assume anything about a population. I don't care. There's no population to work with. Instead, it's just samples. And I find this rather appealing because some of the problems with null hypothesis testing is we build it upon these assumptions that are just sort of ridiculous. Like, sometimes we do care about a larger population, right? But sometimes I don't, right? So when I'm looking at my faculty evaluations, they're about me. I don't really care about the larger evaluation pie in the sky because that's not really the point of what I'm doing. So if we don't assume there's a population, we don't really have to worry about how the population that isn't there is structured. And really the biggest thing about null hypothesis testing is that it's about parameter estimation. So we're estimating the parameters for these populations, and we're testing if they're different. So I might assume that the tests, the classes that I teach in R have a different parameter than the classes I teach in SPSS, my evaluations. Or I could just say, like, I can just estimate the mean and see if they're different. Right? So the goal of a permutation test is just to test if effects are different. And that word effect is pretty important. You'll see that. It's not testing if the means are different or the parameters are different. It's if the effects for each group are different, which is a nice way of sort of blanket testing. You could test if the variances are different or if all kinds of things. But it's to test if the effects are different for each group, which might be the means. But we're not estimating those parameters. We're just testing if the groups are different somehow. And then finally, to kind of end on a little bit of background stuff, some traditional null hypothesis testing, the null hypothesis is that two means will come from the same population and thus they have the same mean. I'm doing an independent t here. Or it might be dependent t, but either way. So two group means are from the same population, so they have the same mean. But if we don't care about populations, this null hypothesis doesn't really work for us. Instead, and I took this quote from Hal's website, which he took from Edgington's book, so I've tried to cite it from the original source, and it's really nice, and it's about no matter what test statistic you're using, if you're using F, using T, whatever you're using, there's no differential effect for treatments for any of the subjects. So it doesn't matter if the subject is in treatment 1 or treatment 2, there's no differential effect depending on which treatment they're in. And that can seem like, well, that sounds the same, but it's a subtle shift away from these two means that I've estimated, so I've kind of averaged out the subject, come from the same population, so they're equal means, versus no differential effect for me depending on which condition I'm in. So these are different approaches to effectively the same idea. So they're different focuses on testing if things are the same or different. But null hypothesis testing requires us to build that there are populations that we're referring to and that there are assumptions on these populations, where permutation tests really to say, something different doesn't happen in the null hypothesis. Now, I have always thought about significance testing, it's kind of this weird Frankenstein system where we are rejecting the null to accept the research. Now, we don't ever say that because we're good scientists, but we are rejecting the null hypothesis, so the only thing left is the research hypothesis, which is that there are differential effects. And so we could still use those ideas. And I call it the Frankenstein system because if you look at the history of traditional null hypothesis testing, you'll see that it's not really traditional. It's like half of Naaman Pearson and half of like some other people, Fisher's test, and so it's kind of this weird system that we've put together that is clearly not really working very well. But we can still use those ideas of like, I'm going to reject this null, that there's no differential effects for treatments. It's just that we're not referring to this larger population where the groups are in the same, big group population. I think permutation tests have a nice, like, simple quality to them, so I don't even know that I need this sort of system. I can just say there is a differential effect or there isn't. So how do they work? So the basic logic of them is that I have my real data with either levels or conditions, right? So I have my real data set. You can actually do regression models too. We're going to focus here on categorical groups. And I test that real data. So I get my test statistic. Because the math behind ANOVA doesn't necessarily mean that you have to use our null hypothesis testing stuff. I mean, ANOVA math just is the math itself. So least squares and hypothesis testing are not the same thing, right? So I'm going to test my real data, and then I'm going to take that data and shuffle it. So I'm going to randomize my data. So sometimes these are called randomization tests. I'm going to test my randomized data using the same test statistics. So I might run an ANOVA on the first one, get my real number, and an ANOVA on the second one, my randomized data. And then we'll just calculate simply how often does our randomized data statistic, so this might be F, it might be T, exceed the real data statistic. And so that is gloriously simple. You take your real data, you shuffle it, and you test just how many times out of 1,000 or how many ever you want to run. The example I'm going to give you automatically picks a permutation number. How many times does it exceed, like your randomizations exceed the real data statistic? And so that gives you a probability, so it brings back into things that most of us are familiar with. And it's the probability of getting your real data statistic giving a random shuffle. Right? And so that's nice because if the data is random, like in your real data, if there's no difference between conditions, it wouldn't matter. I could randomly shuffle people around and I would get the same set of statistics. So the idea is conceptually pretty simple. If there are no differential effects, it doesn't matter which group we put people in. A random shuffle will give me the same results. And so I'll have a high p-value because the probability of getting random results is the same as the probability of getting this result. Okay, I probably shouldn't have said it that way, but it's the idea of like, we're going to get as many random results as we are this real result because there is no differential effect for groups. If there is a differential effect for groups, what we'll see is that our real statistic is much higher. So the probability of getting something even more extreme is pretty low. So you won't see as many high values, assuming your statistic is high, as you do a random shuffle. Now, notice what we're not doing. And this to me is like the real crux of the difference, is that we're not comparing our data to some theorized null distribution. So if I'm running ANOVA, what I do is I test my real data, I do this first one, and then I just skip all the rest of this because we've already shown all these different tests on what we would assume the cutoff F score would be if the data weren't different. So we pull out our chart, or honestly, we just use our p-values that are already there for us. But if we were in a baby stats class, we would pull out our little chart, we'd find our degrees of freedom, find our cutoff F score, and we compare. So this is a null distribution that we have, already kind of theorized that this is the line in the sand where it's significant and not. What we're doing here is we're just testing. Like, what's the probability of randomized data exceeding this statistic? If the probability of randomized data is pretty high, that means that, well, this is probably pretty random. And I don't need to use p less than 0.05. I could pick my own, but most people are still using 0.05, so I'm going to do that for the rest of the example, just to kind of like compare and contrast on how these are different. But I'm not comparing my data to any type of null distribution, because there's no population involved. Instead, I'm comparing my data to randomized data. Also, side note, this is not to be confused with bootstrapping. Bootstrapping is a different monkey altogether. Okay. So I'm going to give you an example. And mostly because it's that time of year where faculty get evaluations on their classes. And if you teach statistics, you will understand this, that students hate this class. People really just don't love the statistics class either way. So it is difficult to get high evaluations when you actually give real tests and students don't want to be there. So I have taught my undergraduate statistics course in both SPSS and R, and there's my perception that the evaluations have changed when I switched from doing a point-and-click system like SPSS to a more programming system like R, because, oh my god, I have to take stats and I have to learn how to program, the world is ending. So is there a difference in my faculty evaluations? I did cheat a little bit. There actually isn't. The means are very similar. People just don't like statistics in either form. But I think just to get the point of what's happening here. Okay. So if I were thinking about assumptions, some population of faculty evals out in the world. So let's assume that there's this group of faculty evals that mine are coming from, which makes no sense if you think about it, because I am me. And so I guess the population might be my larger set of faculty evaluations. But so there's not really like, what would that population be? I don't know how I would define that, because I certainly don't want to compare myself to other faculty members or first-year graduate students teaching this class, or people who are teaching it by hand. So we still have some faculty who teach how to do all of this by hand. Okay, kitty cat, come on, get out of the way. And then if you've looked at faculty evaluations, you know that they are not normal in any form. They tend to be skewed towards the top, or if they really hate you, towards the bottom. And I don't know how homogeneous this data really is. So I calculated, I have this data, you can download it from our website, but you have to give me a couple days to put it up because we're working on redoing stats tools. But I pulled some real faculty evaluations from my old data, and then I edited some so that they would actually look different, even though they're not probably statistically different in a traditional sense. So I pulled the data set here, and then I just calculated the means here. So it looks like my R group is giving me a much lower mean, with this question being, this course is in the top 20% of all courses I have taken, which is just a ridiculous question, so never mind that. And it's a 1 to 5 scale, where 5 is, yes, this is the greatest course I've ever had in my life. This class I didn't want to take. So they look different, right? That's a half a point on a 5-point scale. So for me, that is a little concerning. Then I look at my standard deviations here, and they're, okay. But that might be fail like a Levine's test, depending on sample size here. I think there's only about 20 people in each one, so probably not going to fail Levine's, but, it looks a little different. Some of this picture will come up larger, but so calculating the distribution for my R group here, looking at their ratings, it's clear that they're skewed towards the top, and that the spread is from 1 to 5. So some people really didn't like the class, and then some people thought, oh yeah, this is a great class. Okay. And so that is not a normal looking distribution in any form. And I don't have enough people in this particular set of groupings to calculate a normal distribution. Okay. If I look at my SPSS one, this might be difficult to see because the graph came out kind of small, but it actually only ranges from 3 to 5. So the distribution is definitely skewed towards the top, and is not as wide of a range as my R distribution. So I'm not really hitting normal here, and I don't really know who the population is. So do I even care to run this in a traditional manner? I did, so you could see the differences. So I ran just a basic independent t-test, and I turned on equal variances just so I would get the normal t and not a Welch corrected t. So remember in R, if you leave that var.equal off, you get a Welch Satterthwaite correction on degrees of freedom, which changes your p-values. And what it shows me is that my t-test here is not significant in a traditional p less than 0.05 sort of way. They're getting close, right? If you want to talk about marginal or trending values, which is another problematic situation. Not that I totally meant this lecture to be about the problems with null hypothesis testing, but it kind of fits naturally here. So I guess I would say this is not significantly different, right? But it does, like the numbers wise, look different. So this will be our traditional t-test, but pay attention here. We're going to focus on the p-values to show you how the difference is between these two things. Now what I did, oh man, it cut off the bottom. I'll run this separately here in a minute. Maybe make it smaller. This is the part I haven't totally figured out, is how to control the sizing. And how it's made, and now it's mad at me. There we go. Okay, so now you can see everything. So the independent t-test I did using LMP. You can also use AOV, which I'll show you on the next slide. But so LM, your traditional LM for linear model, P for permutation test. All of this is in the library LM Perm, and it makes it like stupidly simple, which is great because that's why I love R. So what you have to do is save the output and then run a summary, or you won't see all of the numbers I've got here. Right, so I ran this as an LM just to show you the LM options, and it's the same setup. So it's Y is approximated by X here. Your perm option here, there's exact, prob, and SPR. I think the two that you'd want to use is either exact or prob. If you're using exact, you need probably a smaller sample size because exact will give you every possible permutation of your data. Prob will give you a good estimate, and then I don't totally get exactly what's going on with SPR. So I would recommend the first two, and then if you like the last one because you understand what's going on, go for it. SEQS sequence here, or sequential. This is going to be more important for two-way ANOVAs because sequential is the type of sum of squares. So sequential sum of squares is like, I think, either type 1 or type 2 sum of squares. Most of us are used to using type 3. Which is unique sum of squares, so I turned off sequential. The default is actually to leave it on, I think. So if you're wanting to compare your results, don't run easy ANOVA, which I'm going to show you in a second, and then leave sequential on. But if you're using AOV or LM, it actually will run sequential sum of squares unless you do some other stuff. All right, so it told me which one I ran here, so unique sum of squares, because that's the least squares math that I've got my head in, and then I just ran a summary of that output. Now this gives this to me in traditional regression style, and so it gave me an estimate here of the difference between the two, but here's my p-value, right? So my probability of the difference between those permutation estimates is 0.17. Now, if I look at my ANOVA statistic down here, it's going to match what we had on the previous slide. So what will happen is, like, every time you run this test, it actually will give you a different answer because it's a permutation test. All right, the other way to do this is AOVP, and this is probably going to appeal to people who are dealing with categorical data. But the setup is the same because AOV and LM are actually the same math, right? So I've got Y is approximated by X here, and then the same two options. Okay? But the output here is what gives you a different picture. So I can now look at my more traditional ANOVA table. And here's where my p-value, I'm going to compare back 2 slides here to the p-value for my t-test. Okay. And so they're actually giving me roughly the same answer, although I don't know that that's always going to be true. So I could run this t-test or AOVP several times, and you're going to get different p-values here because of what it's doing. It's permutating in different ways. It did run 970 iterations for this p-value here. And then I could report this in a traditional sort of F statistic way. All right, now the more tricky one here is two-way ANOVAs. So I made up some fake data on who was male and who was female because I've found that teaching this class over the years, it's 90%, sometimes 100% female. So I've had semesters where I've had no men. Which is good for jokes, but maybe not good for why are there no men in my class. But and so I just kind of added some fake male and female markers, and it looks like if I were just eyeballing these numbers and not really considering variance, it looks like in my R group the females really don't like it, and the males like it more, and then my SPSS is kind of flipped the other way. So it kind of creates an interaction picture. But then with those standard deviations, they're all about 1 point from our group and a little less from my SPSS group. Now, if I run a traditional two-way ANOVA, I love the easy library because it just gives me more control and I just am a fan. So I ran this as an easy ANOVA. So we do data, it's my permutation data. Within subject's ID, everybody's got to have a participant number, even if it's between subjects. My dependent variable is what rating they give the class. My 2 between subjects variables are class and this type of student, that's male and female. I would like to see type 3 sum of squares, because that's what I'm used to. And detailed equals true just gives me more output. It does show me Levine's test, so I actually don't have to worry about homogeneity. But again, what population are we comparing this to? And then I get my 3 different F statistics here. And they're all very small because this is fake data. And I would say that none of these are really significantly different. So these are the p-values. So that first one is still around 0.10, at 0.4, and 0.11. Okay. But I do like effect size, and these effect sizes are nothing to sneeze at. So in my made up data, I still made up medium effects. Okay. So if I were looking at this as a researcher who's focused on null hypothesis testing, I might say, well, they're not significantly different, but the effect sizes are worth investigating. We should do another study with a larger sample to see if it holds, right? So we don't got encouraging p-hacking here, where I go, well, this effect size is actually a big deal. I should just add more people. We should do another study and see if it holds. Now, if I want to run this as a permutation test, so it's AOVP still, Y is approximated by the interaction between the two. So I've got my little multiply here to give me the main effects and the interaction. And then I told it to do exact. Now I'm using exact because I have a small data set. If exact blows up your computer, try prob. And I get the same sort of output here. And I actually get numbers that are a little bit better, if I think about better as in terms of significance values. So a little bit lower than the p-values for these ANOVAs. But if I were to run this again, I might get different numbers. So my 0.08 matches approximately. This is a little bit closer to being significant. And this one is approximately the same. So there might be a small interaction here, depending on how you want to talk about p-values. But this table should be appealing to people who are used to seeing traditional ANOVAs because it looks like a traditional ANOVA table. And I could report these numbers, but there's no F here. So you'll notice that you got sum of squares and mean square. And I could calculate F, right, the division. But I think here just reporting your like your iterations and your probabilities, or even you could report the whole box. But people are probably going to want something to compare it to. So I don't know a good way to report this yet. That's one issue that I see, is that you're working with traditional folks, but you want to use this new, it's not new at all, but you want to use something different. The hardest thing is always explaining why this something different is better. So you could report just the p-values, you could report the number of iterations, or you could do the fantastic thing and include all of your data and output, like on an open science website, so people can look at it themselves, with the warning that if you run this again, it will give you a different answer. So here I could say that the likelihood of this interaction, a randomized data set being greater than this interaction, so randomized data having this interaction, is 0.07, okay, if I round up. So 7% of the time, a randomized data set will give me this same interaction that I see in my data. So I might decide that that's important or not. So kind of in summary, it's really a difference in focus. I am focused on this sample. I don't care about some population pie in the sky. If you read Hal's website, he talks about we don't think statisticians sit here and dream about populations and perfect normal distributions. Really what's happening is we're down here dealing with dirty data, and we just don't know how necessarily to deal with very skewed data in an appropriate way. So if you don't care about populations, this might be a good alternative for you. It's a focus on the sample and not really caring so much about maybe a larger group, or maybe you have so many people in your data set that you're like, this is representative, but maybe we want to try a statistic that doesn't rely on these populations and assumptions. And I think that's important because often people see non-parametric statistics as like, oh, well, your assumptions don't meet, do non-parametrics. In non-parametrics, like let's say a Friedman's test, people are still using this assumption of some population, but we don't assume that the population is normal. There's still this like estimation idea behind it. And so the biggest concern I think you should kind of focus on here is like explaining this as a focus on the sample and explaining what a randomization test is. But also remember that randomization tests, especially if you're using a probability estimator, is going to change each time. And so being careful not to run the results until you get the answer you like. And so this is where I really want to push the Open Science Foundation and putting your stuff online so that they could run it themselves if they wanted. But that's a very brief and not at all thorough investigation of permutation tests, just an idea of like how they work and how easy they are to run in R, and then just a way to understand what the big difference is between the null hypothesis testing focus and a permutation test focus.